We've looked at a Ka where we were given the pH, which is an equilibrium measurement, and allowed us to calculate every change that's occurring with the substances that are involved in our equilibrium constants. We'll come back to weak bases, but this is a very tricky problem, which can be done multiple ways. But I'd like to introduce a method of approximation. In this instance, we have a weak acid and a pH that is not given, but instead we have a Ka. We're being asked to calculate the pH of a known concentration of an acid whose equilibrium constant we know. We begin with the dissociation of, in this case, acetic acid, also known as ethanoic acid. We have water. We now have the acetate or ethanoate ion, and we have H3O+. Notice this time we are attempting to calculate the equilibrium concentration of each species, but it is the pH that we want to report for our final answer. So let's proceed. With two simplifying approximations. Our first. What I mean by this is that if something is a strong substance in chemistry, then it reacts completely and it goes away. If something is weak, it's going to remain in that form, essentially. That has an impact on how we proceed with the math, but we will come back and figure out whether or not this is true. Now, what do I mean by two less than symbols? I mean that we're talking about orders of magnitude smaller. I am going to show you that Ka is less than 1 over 100. In fact, it's a lot less than 1 over 100. But that is what we mean when we see two, in this case, less than symbols. Two greater than symbols has the opposite meaning, but the same general idea that we're talking orders of magnitude, not just a little bit bigger. Okay, now acids create acidic solutions. This means that the concentration of H3O+, when we have reached equilibrium, will be so much greater than 10 to the minus 7, that 10 to the minus 7 becomes insignificant. This has an implication right here. I'm simply adding x. I don't have to worry about subtracting out the 1 times 10 to the minus 7, and then in my x's, I'm going to have to subtract that off later again. Nope, we're fine. Because we formed H3O+, because the stoichiometry of this reaction is one of those 1-to-1-to-1 things, we know that we've got plus x for the concentration of acetate ion. Now, this is minus x, but we come back to our first simplifying approximation, and we will write 0.2. The change in acetic acid is so small that it is beyond the significant figures to which I know acetic acid. I'm ready to proceed. I now know that 1.80 times 10 to the minus 5 Ka is equal to concentration of x. Oh, why am I making concentration symbols? I don't want to do that. X is my concentration, so I don't need square brackets. X times x divided by 0.2. X being the concentration of hydronium ion, which I'm solving for. Because of the balanced equation, X is also right here. It is the concentration of the conjugate base. And my simplifying approximation is that I have a weak acid, and therefore the change in the concentration of that acid is insignificant, and we can justify that later. This means that X is equal to 0.2 times 1.85, 1.8 times 10 to the minus 5, that I'm taking the square root of this whole thing. This gives me an X of 7 times 10 to the minus 3. 1.9 times 10 to the minus 3. Now, this is the concentration of H3O plus. It is also the concentration of the conjugate base. The conjugate base in this instance is not going to impact the pH, so I take the log and I change its sign, and I report that my pH is equal to 2.72. Okay, now we go back and check. Is it true that 1.9 times 10 to the minus 3 is much larger than 1 times 10 to the minus 7? By 4 orders of magnitude, it certainly is. So we could have started with 0 right there and been just fine. We already know that Ka is much less than 1. We were given that Ka. That Ka is right here. And we now see that our X, which is 1 times, let's put it in standard notation right where it belongs. That number is 0.0002 approximately, meaning that at equilibrium, we actually had 0.19. Interesting. This isn't exactly the same. But I'd like to introduce you to the rule of 5%. A 5% error represents an incredibly successful experiment, and in our case, an incredibly successful problem solved. So I notice here that 0.002 is 1%. 1% of my acid has dissociated. That is less than 5%. This is a completely acceptable answer to the question, what is the pH of this? Oh, excuse me. This is a perfectly acceptable answer to the question, what is the pH of the solution? A 1% error will not impact our final answer in terms of the concentration of H3O plus and therefore the pH. This is a weak acid whose Ka is known, and we use an approximate method. That approximation is right here. Our concentration of H3O plus is approximately equal to the initial concentration of the acid times the Ka of that acid, all under the square root symbol.